Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we inject weird and wonderful science directly into your genes. I'm Ian Woolf. On this edition, fresh scientists take the Bright Sparks Challenge to explain their research in the time it takes to burn down a sparkler. But first up, here's news about Puppeteer fungus. Fungus in ants' clothing. In 2011, we heard about how the Ophiocordyceps unilateralis sensu lato fungal parasite made carpenter ants into zombies, so the fungus can reproduce. The fungus infects carpenter worker ants and then makes them climb tall plants so that the fungus fruiting stalk can burst from the ant's head and spray fungal spores onto fresh ants from a greater height to start the cycle again. Biologists had thought that the fungus took over the ant's brain and used chemical manipulation to make the ant want to climb the tall plants and grab the branch with their jaws before they're killed by the fungus. However, when researchers at Penn State University created 3D images of the inside of the fungus-possessed ants, they were surprised to discover that there was no fungal infection in the brain right up until the fungus in the ant's body killed the ant. Instead, the fungus infects the ant's muscles, encircling them to create a network that operates the ant like a puppet, a fungus nervous system network. The fungus knows how to operate the ant's legs to make it climb plants and clamp on tight with the ant's jaws. The whole time, the ant is free to watch what's happening, but can't resist the takeover of its body by the puppeteer fungus. The Penn State team looked at cell-level interactions between the parasite and its carpenter ant host at the moment in the parasite's life cycle when the manipulated host fixes itself permanently to vegetation by its jaws. They infected carpenter ants with one of two fungi, either a common fungal pathogen of ants or the puppeteer fungus. This way they could ignore common chemicals secreted by fungal infections that don't move the ants around from the chemicals that might be involved in directing the ants' movements. The researchers created 3D images of the inside of the ants using serial block-face scanning electron microscopy to work out the distribution, abundance and interactions of the fungi inside the bodies of the ants. This microscope contains a precision microtome inside. Researchers took slices of tissue at 50 nanometers and captured images of each slice using a machine that could repeat the process 2,000 times over a 24-hour period, stacking the slices for the 3D model. Colleagues from the University of Notre Dame then employed machine learning algorithms on the images to train computers to differentiate between fungal and ant cells to work out how much of the organism is ant and how much is fungus. They found fungal cells through almost all of the ant's body. Senior author David Hughes remarked that there were so many fungal cells that these manipulated animals were a fungus in ants' clothing. Except there were no fungal cells in the ant's brain at all. So instead of the fungus motivating the ant to move its own muscles, the fungus moved the ant's muscles with its own network of fungal cells, like an added nervous system, overriding any commands the poor ant was frantically giving its traitorous body. The researchers suspect that the fungus may still chemically alter the ant's brain, but they're not sure. As to why the fungus saves the brain for last, their best guess is that the fungus may need the ant's brain in order to make the final bite that hangs the ant from the high branch it's climbed before the spore stalk bursts through the top of its head. Or maybe the fungus is just saving the best for last. You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Neil Byrne is the Creative Director of Science in Public, helping scientists present their ideas to the public in plain English. Science in Public is celebrating its 20th year. I visited a pub in Surrey Hills for the presentation of the New South Wales entrance to the Fresh Science Sparkler Sessions, where early career scientists stand on stage and explain their research and the time it takes a sparkler to burn down. You will hear half of the Sparkler Sessions in this edition and the other half next week, with their scientific limericks and haiku in a future episode. Unfortunately, there wasn't a microphone for the audience to use when asking their questions. And their questions weren't repeated on microphone by the host or the speaker, so I will be revoicing the questions so you can hear them. Dr. Lee Dayton, an experienced science communicator, asked most of the questions, and she was one of the judges for the night. Now here's your host, Neil Byrne.
Good evening, my name's Neil Byrne. I'm the Creative Director of Science in Public. So we're a little business based in Melbourne who help researchers present their ideas in plain English. Yesterday, you met journalists from Channel 9, Channel 10, from the Sydney Morning Herald, from The Conversation, and from a radio station, 2SER. There you go. And today, the Freshies learnt about talking to business, government, and universities. But tonight, we're going to keep it simple. We're going to ask them to talk about their work in the time it takes those very unreliable sparklers to burn out. I have an ice bucket. Very important. I have a lighter. I have sparklers. Let's introduce our first freshie, who's going to talk about making batteries from thin air. Jessica Allen from the University of Newcastle. Would you like to come up, please? Yay! It starts burning, but you've got to hold it steady. So, she's a bit nervous, it's shaking.
Oh, this sparkler is making a whole lot of heat from a chemical reaction that's also producing a gas. Much like when we burn coal, we also make a gas, carbon dioxide. Now, this reaction might seem like it's pretty irreversible, it's a one-way street, but actually we can reverse the reaction and we can make solid carbon from gaseous carbon dioxide. Now, who here has an iPhone? Right, everyone. And did you know that most of the material that makes up your battery in the iPhone is made of carbon? But not just any carbon, it has to have special properties that make it good at storing electrical energy. And what we can do is using sunlight and carbon dioxide is we can make this very special carbon even better than the normal carbon that they use for batteries, but it's renewable, we have greenhouse gas emission reductions, and more batteries!
So the essence of this is then that all those batteries need carbon.
Yep.
And that carbon's coming out of the ground.
Yep.
And you can make better carbon and
From the air.
And those are going to be better batteries as well.
They sure will.
And how far from market? When are we going to see this technology on the street?
I'd say it's probably at least 10 years away. 5 to 10 years. Maybe 5.
Maybe
Depending on how much funding we get.
Good. She takes credit cards. If you could just donate to her research as you leave. I have time for one question from the audience. If anyone has a question, I will invite you for each of them just to the one question. We have a question up there. If you could stand up and project.
Why do they make better batteries?
So carbon that's used in batteries has very special properties, and we need to be able to reuse it over and over again. So what happens is lithium goes into and out of the structure and over. And over a period of time, this carbon starts to degrade and it gets worse, which is why you need a new battery. So what we can do when we're actually making the carbon from scratch, it didn't have any precursor, we're actually building it how we want it to be built, is that we can build it in the right structure so that that disintegration doesn't happen.
Thank you very much. Excellent. Thanks for going first. And second this evening, we're going to find out about smoking. We've looked at Yik Lung Chan from the University of Technology, Sydney. Come on up. Excellent. Here is your sparkler.
Okay, 1 second.
Don't inhale.
Ooh, so we know that the sparkle creates smoke, and we know the smoke is really bad. But then what we also know that smoking, mother who are smoking is actually bad for the baby, and we know that it's going to cause lung disease in long term. But what we don't know is how it causes it. So the mechanism we find is basically called rage, as angry as this sparkle. So we are trying to find treatment options to actually calm this rage down, and probably this sparkle is going to burn down. And in that way, we can actually stop those diseases eventually and help to, cure patients with lung diseases. And it's burning.
Excellent.
Actually, still got quite long.
We have time for a question from me. So we know that smoking's bad for you, but what your work is showing is that it's not just bad for you, but that smoking, when you're planning a family, when you're pregnant, when baby's born, could actually lead to emphysema for the baby much later in life.
Yes.
And at quite high levels.
3 times. So basically, other research find that it's actually 3 times higher chance that the baby will have, the baby when they grow into an adult, they will have emphysema easier, 3 times. But what we are finding is we find the mechanism of that. So the mechanism is called rage. So we are trying to think of some treatment that can actually reduce this rage mechanism and make it a better life for the patients.
Excellent. Thank you very much. Any questions from the audience?
Could you please tell us a little bit more about the mechanism of action?
So basically, the rage will induce inflammation in the lung. So this inflammation is a longer term. And also something called oxidative stress, such as it is some active molecules that can attack on cells. So think about it, there are more active molecules inside lung cells, and it will just damage it in the longer term. So for children who are exposed to maternal smoking, they are more prone to this sort of attack because their level is higher already in first place.
Are they exposed to tobacco byproducts?
Yes, during pregnancies.
So during pregnancy, there are epigenetic changes from tobacco byproducts?
Yep.
Good. Thank you very much. Next, nitrogen. Nitrogen is important, isn't it? How important is it? Oh, one word. I say nitrogen and suddenly a fresh scientist appears. This is wonderful. Zhengyu Wen from the Centre for Carbon, Water and Food at... doesn't say where you're from. The Centre for Carbon, Water and Food at what university?
Sydney University.
At the University of Sydney, which still thinks it's Australia's only university. So we won't tell them, if you don't tell them, that there are in fact some other universities in Australia now. Let's get going.
Yeah, let's get going. Hey guys, you don't know that. You see, crops is actually using nitrogen transporters to absorb nitrogen fertilizers from the soil, but our crops doesn't really do a good job. They only use about less than 50% of the nitrogen fertilizer we give them. And that's a big waste of money for the farmers. And we recently discovered 2 nitrogen fertilizer transport proteins in maize, aka corn. And we also found by changing the structure of the protein, we can improve the nitrogen transport rate of these proteins and give them a supercharge. So in a way, in the future, we can grow more food with less nitrogen and less pollution. Is that right? That's right.
Nice timing. Excellent. And in the first instance, what crop are you working with?
Maize, corn.
Excellent. And it's likely to be a GM crop?
We can use a molecular assist breeding program other than GM. Breeding program seems more user-friendly.
Nicely fudged. Excellent. Any questions from the audience? Thank you. Question at the back.
Can you show me a picture of how the crops you're growing are more productive and healthier than the ones from before?
Not necessarily, but you can give them less fertilizer and they can absorb more and grow a little bit faster compared with the traditional crops we're having right now.
And this is in maize.
Yeah, this is in test tube. We're going to apply this technology in the real crops if I got the funding.
Excellent. And there may be a secondary benefit you were saying earlier today.
Oh, this protein can also transport chloride as well, which is a form of salt. And by changing that structure of the protein, we can reduce the salt absorbing ability of this protein and transform them into nitrogen transport ability. So that will reduce the salt toxicity of the crops as well.
Excellent. Thank you very much. That was good.
So can I... Sorry, can I do the
how are we going? So you're ready to go?
Yeah, I'm
excellent.
ready to
So the other thing we're going to ask the freshie, he's got to head off. He's got a flight to catch. Where are you going? Somewhere exotic?
China.
China. Quite exotic. Once we've run through the first 7 freshies, we're going to break for half an hour. And in that break, we want the freshies and their friends and colleagues to write a haiku or limerick about their work as well. Because that's easy. Have another beer, it'll be easier. But as you have to head off, what are you doing? Haiku or limerick?
Haiku.
Haiku. Your haiku, please.
Okay. It's, for me, I'll have to say it's really difficult for a non-native English speaker. I just try my best.
Go for it.
Transporter protein, that's where the nitrogen coming in. That's the research I'm keen and providing foods for human offspring.
Nicely done. Yes. Bit of a rhyme in there. Excellent. Thank you very much. Well done. Thank you very much. Good. So I'm feeling a bit of pressure in my eyeballs. I can't really see clearly. Rona may have a solution to that from the University of Sydney. Come on down. Rona Chandrawati from University of Sydney, and we're going to talk, I believe, about glaucoma.
All right, so what I do, my research focuses on developing a new treatment for glaucoma. So what is glaucoma? It's irreversible blindness that affects more than 60 million people worldwide. So what happens in glaucoma eyes is our liquid flow is blocked, so it creates high pressure. So this is the problem that we need to tackle to lower the eye pressure. I develop tiny particles that can be implanted into the eye that can be instructed to lower eye pressure at the disease site at the right dose and at the right time. So we have shown in a mice model that our particles implanted can significantly lower eye pressure compared to the non-treated eyes that can delay the onset of blindness. Very close.
Nicely done. Excellent. Thank you very much. Any questions from the audience? Just while they think about that. So currently, eye drops several times a day.
Yep.
What potentially, how often would we need to use your treatment?
Yes, so once implanted, it will be stable over months, so at least 6 months. So that will reduce the necessity of having patients to deliver eye drops, which is the most common treatment of glaucoma at the moment.
So you're not going to cure it, but you're going to slow its development.
Yes, and make it more convenient than eye drops.
Excellent. Any other questions? Yes, question down there.
How is this treatment delivered? Contact lenses?
You'll wish you hadn't asked that.
That is the difficult question. So it will be implanted, so it's through injection into the eye.
Yeah, you see, like, injection, I got no issue with that. You're going to stick a needle in my eye? No! but only once every 6 months, potentially.
Potentially.
Good. Thank you very much. That's fantastic. Pop your sparkler in there. Thank you. Who have we got coming up next? Ooh. Photography. Forensic technology. Xufeng Lin from Charles Sturt University. Excellent. Come on up. Dramatic tension. There it goes.
Okay. Nowadays, images and videos can be easily manipulated. This is casting doubt on the credibility of images and videos and give a rise to internet crimes. So we have developed, is there any way we can verify the credibility of images and videos? We have developed a technology to extract unique fingerprint information of cameras from images and videos. And this technology has been successfully used to help UK police to investigate a real case. Which led to a 9-year sentence for a suspect. That's it.
Wow. That was excellent. So, because over the last couple of days, you've had a somewhat longer story.
Yeah. Big shot.
But you had it all there. You had the essence of it. You had the essence of what was possible, and I'm sure that has generated at least 1 or 2 questions. Any questions? Thank you.
How do you verify the images?
I actually have a software daemon on my laptop. If you have interest, I can show you how we can use it to verify or detect the image forgeries. Yeah.
And
be a little bit more clear about the nature of the fingerprints.
The fingerprint is, every human being has a fingerprint, right? But our fingerprint is a physical fingerprint. But the camera fingerprint is digital fingerprint, invisible. It's based on the statistical images of images. So it's really hard to get rid of it. So if you did something back with a cell phone or camera, it's better to throw your cell phone as soon as possible. Yeah.
So there are variations in the processors or the interaction between the image processor and the other bits of the camera. Where's the difference coming from? Why isn't every smartphone, why isn't every iPhone 22 exactly the same?
That's due to the imperfection of miniaturization process. So it's really hard to control the process of making every pixel. So there will be always a slightly difference between different pixels because there are a huge amount of pixels. So this makes it very random and unique. This can serve the same purpose as our human fingerprint.
So it really comes down to that every camera is just that little bit different.
Yeah.
There's enough variation
that
you can find that variation
and
track it back.
Yeah, that's right.
And this first case was the Surrey police. Sussex police.
Sussex.
In the UK. So already in use. Excellent. Thank you very much.
For this week's Bright Spark Challenge, that was Jessica Allen talking about carbon for batteries from thin air from the University of Newcastle. Yik Lung Chan from the University of Technology, Sydney, about the effect on babies of tobacco use by their parents. Zhengyu Wen from the University of Sydney about improving nitrogen uptake in plants using less fertiliser. Rona Chandrawati from the University of Sydney talking about glaucoma treatment implants. And Xufeng Linfrom from Charles Sturt University with forensic verification of digital photos and videos. Listen for the final round of Bright Sparks next week.
They were seldom bored with anything. They were constantly building up stores of information in active memory banks. When confronted with a specific need, they would call on these memory banks for information, which they would run through, sort out, and relate to the problem at hand.
And that's all from us this week on Diffusion. Would you like to hear your voice on radio? Record a voice memo on your phone or use the voicemail tab on the website. Somebody should try it. We need more people contributing stories to Diffusion. Send your contributions, opinions, helpful suggestions, and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please do send me an email so I know you're listening and you'd like to hear more episodes. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. Join my patrons in supporting the show at patreon.com/diffusionradio. The news music was Rynos theme by Kevin MacLeod of incompetech.com. Sound check and fact checking by Charles Willock. I produce Diffusion, which is broadcast around Australia to 27 stations on the Community Radio Network, including 2 RBM in the Blue Mountains of New South Wales, 8CCC in Alice Springs and Tennant Creek, 2 NVR in Nambucca Valley, and 3 MBR in the Mallee Border districts of Victoria and South Australia. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to our podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed this show, you can explore more than 900 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Subscribe to the Diffusion YouTube channel at youtube.com/c/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.